Good afternoon. Welcome to course Thermodynamics of Materials. Today we are into lecture 189 and 190. So we have just started assignment number 13 last class. In the last class we have solved problem 1. So today we will take up problem 2. So more I see you see here I have written 5 problems based on Gibbs Phase Rule and stability diagrams. That is about assignment number 13. So one already over. So today we'll take up problem 2 and problem 3 and okay, if possible problem 4 also. So this is the problem I've already written down here. Uh, this is what the part A is. We want to reduce solid tungsten oxide by an carbon excess of carbon, okay, by an excess excess of carbon to produce metallic tungsten according to the following reaction. Tungsten oxide plus carbon goes to tungsten plus CO plus CO2. Just not balanced, it is not required also. Just the phases involved in the reactants and products or species involved. Make a phase rule analysis and find if the reaction takes place at a unique temperature or over a range of temperature when the total pressure of the system is fixed, say at 1 atmosphere. This is the first part. So let us start solution. Okay. After this part is over, then I will take up next part, part B of problem 2. So what is this actually? See, make a phase rule analysis. You have to consider the Gibbs phase rule. C minus P plus 2. F is so C is how many? This is actually, I tell you what, this is 3 phases and 1, 2, 3, 4 plus 2. I will explain why it is C is 3. C is 3 because it is tungsten carbon oxygen system. C is 3 and P is 4. You actually, as you see, if all phases including the gas phase, all condensed phases, solid phases and the gas phase are in equilibrium, then P is 4. What are the P is 4 actually? 3 solids, which are the WO3 say, WO3, WO3, then W and carbon. These 3 solids and the gas phase which contains CO2. So this is actually about P is 4. Then what is the result? Degree of freedom is 1. So, so what okay, P is 1. So, and 1 is fixed already by the problem. It is P is 1 atmosphere. Total pressure of the system is 1 atmosphere according to the problem. So how many left? None. One already used up. So none left. So it should be unique temperature. But there is one puzzling thing. What is the puzzle? That we want to reduce solid tungsten oxide by an excess carbon. By the way, this figure, oh, I'm sorry, this is figure 2. Please don't consider these figures now. And this is figure 3. This is figure 3. This will be about the second problem. this will be relevant to the say problem 2. Oh, problem 2. I'm sorry. I'm very sorry. Problem 1 already. Okay. Problem 2. This is about. This is actually this problem 2 has no figure. Has no figure. Problem 3 figure I for problem 3 figure 2 will be relevant, and problem 4 this figure 3 will be relevant. This is actually, so don't consider this. This is for the next problem, and this is actually next problem. Okay, this one. Okay, so I've actually kept the, so we may actually make a fencing here better, so we understand that this is okay, and here also, yeah, this is okay. These are for subsequent problems, not for this problem. No figure, no figure. And problem figure 1 was for the last days, yesterday's problem 1, that figure I gave actually. So segregation of copper. Okay, so this, so when this is 1 is expanded, utilized, so no degree of freedom is left, means that temperature, you have no choice on temperature. That is unique temperature should be the answer, but it is not correct, because we want to reduce. So tungsten oxide, WO3, tungsten trioxide, is supposed not to be present. Suppose not to be present in the system. It will be reduced. It will reduce to this. So however, it is better you write this. However, we want to reduce. We want to reduce solid tungsten oxide, solid tungsten trioxide, that is to remove it, that is to remove it from the system, that is to remove it from the system. And after reduction, after the reduction, so after reduction, okay, the equilibrium will have reduction. See, we can have all phases present, that is possible. No, all phases present, nothing is eliminated, no phase eliminated, that is possible. But then tungsten trioxide is also present, but our actually say practical interest, importance, okay, our interest is what? To reduce tungsten oxide to produce metallic tungsten. Take up that problem. So it is supposed not to be present, not supposed to be present. If that is the case, then what is the degree of freedom? And what is the, if there is a choice of temperature, even when the pressure is fixed arbitrarily 1 atmosphere. This is the problem whole. So because this is our importance is this, okay, that because the problem asks us, if we are interested to reduce tungsten trioxide, that means it will be removed from the system altogether, just remove out. So in that case, if reduction, then also, yes, remember, after reduction there is also equilibrium, all are equilibrium, and degree of freedom, the phase rule will apply, okay, including everything in equilibrium, excluding one of them is also another equilibrium. Remember, I always often draw this. Actually, you may see this here also. Okay, say here. This is say copper sulfide, copper sulfide. This is along this copper sulfide both. This is the equilibrium. this is actually a stability diagram. This is actually PSO2 increases, or simply PS2 you may consider also. PS2, since I am not this, just consider sulfur potential increasing. So copper will be eliminated and copper sulfide is alone is present. So say along this line both are present along with the gas phase, say PO2 here. This is equilibrium. So all phases are equilibrium. Okay. It is better if I write this. I can give you PSO2. So this is already known to you. So copper plus SO2 is copper plus O2. Okay. So all phases are present along the line. This is an equilibrium. This is a stability diagram. Stability diagram. A part of it, relevant part. Stability or equilibrium. Remember, stability or equilibrium diagram. So problem. So this line is satisfying or everything is okay. But it does not mean that if one phase eliminated, this is not equilibrium. This is not a non-equilibrium situation. This is also an equilibrium situation. How? If you increase SO2, then copper will be eliminated and copper sulfide will be present, will be stable. So this is the situation. Copper sulfide and the gas phase. Copper eliminated, copper is not there. Conversely, if you increase the oxygen pressure, so copper sulfide will be converted into copper. Copper sulfide eliminated. That is also equilibrium. So this is actually two solid equilibrium, two solid phase plus gas phase equilibrium. This is what? One solid, namely copper sulfide, solid plus the gas phase equilibrium. This is also one solid, namely copper plus the gas phase. So all are equilibrium. Okay, this is remember this. So this is so this is actually the entire diagram is stability diagram. So I am removing this. Okay, so this is actually so we are considering equilibrium after the elimination of tungsten trioxide from the system, because our interest to reduce it to produce metallic tungsten, the valuable thing, metal production. So after the from its oxide, after the reduction, the equilibrium will have the equilibrium will have 3 minus 1 is 2 solid phases, What are they? Tungsten and carbon. See here, tungsten trioxide out. So tungsten and carbon, two solid phases plus the gas phase, two solid phases, actually plus the gas phase of course, two solid phases. So in that case, if that equilibrium, the new equilibrium, if I may say, the new equilibrium after reduction, the new equilibrium will have two solid phases plus the gas phase. In that case, what is the F? Now check how many degrees of freedom, because that is actually asked in the problem. F will be modified. F is C minus P plus 2 again. F C is what? C cannot be changed. 3 minus phases how many? 2 solid plus 3 plus 2. Let me write. C is 3 tungsten as before, and P is 3 is what? 2 solids and the gas phase, which is CO2. Two solids and and the gas phase CO2. So what is the value of A? 2, 2, out of which 1, or in the according to the problem, pressure is fixed. P is 1 atmosphere. Of these two, one is P is 1 atmosphere, arbitrarily fixed. Means freedom, arbitrarily fixed. Another is what? Still another left. So it may be temperature. Temperature can be arbitrarily chosen over a range of temperature. Can be arbitrarily, freely. Arbitrarily means independently or freely. Can be arbitrarily fixed. Arbitrarily chosen. When it is chosen, it can be a range of temperatures, a range of values. Over a range of temperatures. Over a range of temperatures. This is the answer. This is the answer. This is the answer. So this is actually the part A. Part B is what? Part B. Let me write this problem. If we want to have 4 solids, shall I write here? Right here. If we want to arbitrarily chosen, this over a range of temperatures. So if we want to have 4 solids, 4 solids, what are this? WO3, carbon, as you see, tungsten previously. These 3 consider in addition tungsten carbide. So tungsten carbide is present in the system. If we consider this, that these 4 solids are present, and 4 solids and the gas phase, What is the gas phase? CO2, CO2, and if necessary, can actually, it is actually the way I wrote this, CO2 may consider this, and the gas phase CO2. Oxygen will also be present also. Where if you have CO2, you have also oxygen. So you can include this. You may include or you may not. That depends upon how you want to consider the gas phase, composition of the gas phase. Anyway, no problem. You just you have, when oxygen is present, a species increases, you have another equilibrium, additional equilibrium, like CO plus half O2 is CO2 involving oxygen, the neon. No problem. Otherwise, it will not affect the answer. So and the gas phase together at equilibrium, then the question is, do we have a choice of pressure or temperature, or both in defining the equilibrium state, the equilibrium state? Question mark. This is the question. So just you consider. The tungsten carbide, like say, since carbon is there, tungsten carbide is also a possible phase. If that is included, then Answer, solution. So make a phase rule analysis. So you can see, so with these 4 phases, 4 solid phases and 1 gas phase. So if you consider that equilibrium, then do we have a choice of pressure or temperature? Pressure or temperature? If it is 1, then you have a choice of pressure or temperature. It depends on your freedom. Okay, it depends on you. So whether you choose pressure or temperature, that means if it is 1 and or both, I choose pressure freely, independently, and temperature also independently. Means that is possible when there is 2 degrees of freedom. There is 2 degrees of freedom. There is 2 degrees of freedom. Then we both. Look, this is a question. Do we have a choice of temperature or pressure or both? Answer. Solution. F C minus P plus 2. C is how many? Yes, like last time, it is tungsten, carbon, and oxygen, 3 component system. How many phases? 4 solids. C is 3. It will not change. Tungsten, carbon, oxygen as before. We note this. P is 5. Why? 4 solids. 4 solids plus 1 gas phase. What is the degrees of freedom? Is 0. Oh, ho, ho. No choice. No choice. Okay. Far from choosing both pressure and temperature, it is not even pressure or temperature. You don't even 1 degrees of freedom. You have 0 degrees. Means no choice. It is an invariant equilibrium. All are automatically fixed, dependently fixed. So no choice. Do you have a choice? Do you have a choice? No choice. So it is like this. So the system is invariant. Shall I give a star mark here? Just I want to remove this line. Right, nicely, okay, right, nicely. Remove this. Star mark. So the system is invariant. Is invariant, and there is no choice. And there is no choice of any variable, including pressure and temperature. Temperature. This is the answer. This is the answer to the question. So this is problem 2 is over. Okay, with this. So this is very interesting. So let me remove this. I will start next problem, which will relate this diagram. Okay, silicon carbon. Okay, silicon nitrogen oxygen system, that I will consider now. So let us So next problem is so next problem is problem 3. Problem 3A. First part. Pure solid silicon, pure solid silica SiO2 and pure solid Si3 silicon nitride are equilibrated with an oxygen nitrogen gas mixture at 1000 Kelvin. How many degrees of freedom of freedom is F does this equilibrium have? This is the part A, first part. This is A, 3A, this is the subs, okay? Okay, further division, subdivision. So this is the first part of 3A. How many degrees of freedom does this equilibrium have? Okay, and what is the equilibrium state? What is the equilibrium state? What is the equilibrium state? That is the second part. 2 questions already. Next comes the third one. If maintaining the gas composition constant, gas composition gas composition constant, the temperature of the system is decreased to 800 Kelvin, decreased to 800 Kelvin to Kelvin. What happens? What happens? What happens means if there is any elimination of phase, etc. And again another similarly, if maintaining the gas composition constant, again constant, the temperature of the system is increased is increased to 1000. I'm sorry, it was already 1000. So increased to 1200 Kelvin. 1200 Kelvin. What happens? What happens? These are the, so you see, this is actually several division of the problem. Okay, this 3a given is what? Given silicon solid plus O2 gas is silica solid. Silica solid delta G0 is minus 902 triple zero plus 174 T joule, and another one 3 silicon solid plus nitrogen gas 2N2 nitrogen gas is Si3N4 solid. Delta G0 is, it is actually minus 741 000 minus 10.5 T ln T plus 403 T joule. 403 T joule. So the difference is, this is a 2-term expression, this is a 3-term expression. Okay. So this is actually a new thing. So we'll handle this. Okay. This will make the situation little complicated for this equilibrium, silicon nitride equilibrium. But anyway, but we know the principles, we know the rules, we know the relations. So we'll have to take up this complicated issues, and so let us see what happens. This problem is over. So I give you the reference. This problem is taken from reference Dr. Gaskell, okay, and name of the book is, as you know, Introduction to Metallurgical Thermodynamics. Metallurgical Thermodynamics. This is second edition, perhaps. Yes, second edition, page 520. This is the problem. Okay, I tell you 3a, 3b. There is another part 3b that actually is not given in the book, but this has been designed. I have designed that problem, that is later. Okay, so first we solve this problem. Okay, and then I will take up 3b. So the solution. So solution is what? Solution is what? First part, right? First part. Write this. What is that? To find how many degrees? To find the degrees of freedom. Find the degrees of freedom. Degrees of freedom means F. First part. F is, you tell me, C minus P plus 2. How many C is here? You know, C is, let me write it. 3. And how many phases? As we see, 3, 4. 4 plus 2 is house 1. Why it is C is 3? Explain. C is actually silicon. Go by the element oxygen and nitrogen. C 3. Why P is 4? P is 4. Why? Now how many solids? Silicon Si, silica SiO2, and silicon nitride Si3N4. So what are the three solids? And mention this: silicon SiO2, and silicon nitride Si3N4, and one gas phase. gas phase is made up of what and what? Oxygen, nitrogen. So this actually explains C, and C is 3, P is 4. What is the result? 1 degree of freedom. What degree of freedom? It is already given to you as 1000 Kelvin. It is a, this is fixed at 1000 Kelvin atomic arbitrarily. This freedom is utilized. Freedom is exercised. So this is what is this value? This is 1. This is fixed. This is fixed. This is fixed at 1000 Kelvin according to the problem. Okay, this is fixed as specified in the problem. Right, as specified in the problem. So first part is over. How many degrees of freedom? 1. That means if you fix 1, then the system can be fully described at equilibrium. That is required. What is the equilibrium state? The equilibrium state can be defined completely, fully. So this is the second part that we know. Second part, to define to find the equilibrium state. To find the equilibrium state. This must be very easy also. Okay, easy also because we know this. Acha, you start with this. Let us solve this. Okay, so find the equilibrium constant and find the oxygen pressure and nitrogen pressure. Then the system will be fully described. Start. Silicon solid. I am repeating this. Plus oxygen gas is silica solid. Silica solid. This is equation 1. Call it equation 1. And delta G01 is how much? Oh, you consider this. Delta G01 is, we write this, minus 902 000 plus 174 T joule. Okay, delta G0, or delta G0, what it is called? What 1 what temperature? The temperature is chosen as 1000 Kelvin. So 1 at 1000. So substitute 1000 Kelvin for T. So what you will get is, if you do this yourself, minus 728. You check this calculation. 800 is what? Minus 000. Oh, sorry. 000 minus RT ln K. You know, minus RT ln K 1000 K 1000 K 1000. R is how much? You know very well, 8.314. T is how much? What is this? This gives you, or continue here, K 1000 is how much? K 1000 is 1.07 times 10 to the power 38. And what is the expression for equilibrium constant? See, activity of SiO2, solid, activity of solid, these are pure solids, okay, and PO2 gas. This is the equilibrium state, okay. Equilibrium, you may in the suffix you can give this, okay, subscript equilibrium. So what are the values? What is activity of this is pure 1, this is pure 1, so you get or sorry or I'm just writing here, okay, just this star for this, okay, here or PO2 equilibrium is what? PO2 equilibrium is what? If you do this 9.4 times 10 to the power minus 39 atmosphere. This is equilibrium value. Partial pressure of oxygen, very important. This one is out. Similarly, take up the next one, next equilibrium to get Pn2. So let us write this. This is, so you start from here actually, here. Next, so start here. Similarly, write this reaction. 3 silicon solid plus 2 nitrogen gas goes to Si3N4 solid, is what? Delta G0 is what? Minus 741,000 minus 10.5 TLNT plus 174 T joule, okay. So just follow this way, or this is delta G0. Oh, by the way, this is, I'm sorry, this you should label this. This is equation 1, so this would be 2 and this will be what? Delta G0 2, delta G0 2. Delta G0 1, delta G0 2 is this, or you start on this side, or right, delta G0 2, what temperature? 1000 Kelvin. 1000 is what? You substitute these values, you will get actually. So I can show you. One line. Let us write this. Minus 741. Okay. Minus 741,000 minus 10.5. T is 1000. LNT is 11,000 plus 174,000 joule. This is what? How much this comes? Minus 410, 531 joule. This is what? Minus RT ln K, like this. Minus RT ln KT 2000. Okay. And of this R is how much? 8.314. T is 1000. 1000. So this gives you KT 2000 is 2.78. 2.78 times 10 to the power 21 times 10 to the power 21. So give a star here, double star perhaps, double star. You write this side, this side. Use this base. So KT is this, okay. So you get this. Continue. 2.78 times 10 to the power 21 is Kt. Kt, what is the equilibrium constant expression? You write, see the reaction here. Activity of Si cubed. Okay, and what you see? Partial pressure of nitrogen squared. Oh, I am very sorry. Oh, what I am doing? See, this is a product first. Numerator product. Activity of Si 3 and 4, and then activity of Si cubed Pn2 squared. You can give me right at equilibrium. What is this? This is a pure solid, one activity, or you get what, right? Or if you solve this, Pn2 happens to be 1.9 times 10 to the power minus 11 atmosphere. So two answers. PO2 equilibrium, PN2 equilibrium is better, you write. Wait a bit. So these two. So gas composition at equilibrium is completely known, and the rest, the remaining species are pure solids. So it is better we give the answer here. Okay. Is okay. Also right, actually. It is better I remove this. These lines, these are over. These are over. You reference, you have already noted. So remove this. Remove this. Now start here. Use this space. Okay. So this is fine. Okay. So from this, so shall I give it double star, triple star here? Okay. Triple star. So what is the equilibrium state? So this is your answer. Hence the equilibrium state. What? Temperature, pressure, and composition of each phase. That is how you define the equilibrium state. Okay. Temperature is 1000 Kelvin. Partial pressure of oxygen is 9.4 times 10 to the power minus 39 atmosphere. Partial pressure of nitrogen is here 1.9 times 10 to the power minus 11 atmosphere. Yes, okay. And then what is the pressure? Then total pressure is nothing but temperature, pressure means total pressure, and composition of gas phase as well as other phases. So PO2 partial pressure is total pressure is sum of the two partial pressures is what? If we add this to this is much less 10 to the power minus 13, so it will return this value. So 1.9 itself back. Okay, P total is PO2 plus PN2. It will be can give the same almost the partial pressure of nitrogen same as this. Okay, close to this, since this is such a small. So this okay, total pressure. Then what else? This is about the temperature, pressure. Okay, three solids, three pure solids you have. Okay, three pure solids. You know what are they? Silicon, SiO2, Si3N4. What are the, since they are pure solids, so Xi is 1. Mole fraction is 1 for each. So composition, these are pure state. Xi is 1, as you know. Okay, Xi of each solid is 1. Three pure solids, and then what? You remove this line. Okay. Then what else? Gas phase. Gas phase composition. How do you report gas phase composition? How do you report mole fraction? So XO2. How do you report this? PO2 over total pressure. What is the PO2? Right here, 9.4 times 10 to the power minus 39 over total. Total is here 1.9 times 10 to the power minus 11. What this gives? It is 5 times 10 to the power 5 times 10 to the power minus 28. This is the mole fraction of oxygen, XO2. And Xn2 would be what? Pn2 over total pressure. And these both are exactly the same. So all right, 9. What is this? P into 1.9, and total pressure is all okay. Is the same value. So equals to 1. So nitrogen mole fraction. So this concludes. This gives you answer to second part. What is the equilibrium state? This is the equilibrium state. Temperature, pressure, and composition of each gas with their partial pressures means actual composition. So easy. If you know the, see, this is the logic. If you have the, you know the partial pressures of the gaseous species, all gaseous species, then you will get the total pressure by the summation of this partial pressure values. So total pressure is known, and each partial pressure is already known. So what is the mole fraction? Each partial pressure over total pressure. So this is the standard. So so if you know the partial pressure, you know the actually mole fraction also, which is composition. Mole fraction is as fraction, a mole percent. If you want to report, then you have to multiply by 100. Okay. So this is actually. So this is now next take up this very important. This section I'll pick up together. Together. Okay. This one. So for this, since these are all over, so what should I write? Actually, I tell you what. Is okay. So what I do, I remove this. Okay. Now please check. Okay, if this has shifted or anything or same. Exactly, no? No. This one to the right. Right. Okay. No problem. So, it is okay. It's okay. Then thank you. Thank you. 54 minutes. Huh? 54 minutes gone. Okay. So remove this. Remove all this. Okay. PO2, PN2. Okay. I'm sorry. Let us save this somewhere. Save this to important data. PO2 is what? What I've got this PO2 equilibrium. 9.4 times 10 to the power minus 39 atmosphere. Save this, and Pn2 equilibrium is what? 1.9 times 10 to the power minus 11 atmosphere. So just box these two. Okay, these two values may be referred to later on. Okay, when you will take up three. Okay, these two parts, or maybe 3b. Okay, so anyway, save this. Otherwise, you remove this. Remove this. These are all over. All over. This is all over. Okay, so we have actually lot of space now to write the explanations and the answers. Okay, so no problem. Okay, very good. Start. Yeah. So what should I write here? Third part. I call this third part. This third part. Okay, we understand this together. Third part. Noting that you follow answer this. I am giving you the answer briefly, quickly. So what's the question? Wait a bit. Wait a bit. Wait a bit. Wait. See, I give you the answer briefly. If maintaining the gas composition constant, the temperature of the system decrease to 800 Kelvin, what happens? Follow this equilibrium, say one by one. These two equilibrium you consider an effect of temperature. So suppose this equilibrium is there. Now temperature you change. 1000 Kelvin, this is the value, etc. etc. And silicon, Si2 all present. If you increase the temperature, what will happen? This is what type of reaction? You know, exothermic. So if you increase the temperature, that is favored at when you sorry, you decrease the temperature. If you decrease the temperature, decrease to 800, so exothermic reaction is favored with decrease in temperature. So the reaction will move to this. The reaction will be upset. A new equilibrium, silicon, silica, SiO2, oxygen, this equilibrium will be upset, and what will happen? Will move continuously this way, this direction, and until Si solid is removed. So what phase you will get from this equilibrium? SiO2. Similarly, this one, this is also exothermic. Though it is a three term, little bit complicated, but overall you consider this an exothermic because of this large negative value. This you will find out. Okay. So this will also shift to the right. So what will happen? Silicon will be eliminated. But I will explain you. Actually, I tell you what you have actually. So you eliminated what you are getting. SiO2 and Si3N4. They are present as stable state, as equilibrium state, along with the gas composition, and temperature 800 Kelvin. But that will be not correct. Actually, you see, these two also there is a competition. These two are not okay. One is unstable relative to the other. So for this, you have to consider another equilibrium, 3N4 and SiO2. That will consider, and one of them will be eliminated. Or one of them will be eliminated. Perhaps the Si3N4, that I will show. So finally, two phases will be eliminated. One is silicon, another is Si3N4, and SiO2 will be present along with the gas phase. This is the effect of the first case when temperature is decreased to 800. The opposite is easier. Opposite is easier. Why? This is 1200 increased. Temperature is increased. So this is endothermic reaction. This is exothermic reaction. So delta is negative. So favored at lower temperature. Now when temperature is increased, the reaction is not favored with increasing temperature. So reaction will shift in the reactants towards the reactant side. That is the thing. Okay. If you increase the temperature, this is exothermic. So this will be favored in the opposite direction. So silica will be eliminated. And similarly, here the second case, Si3N4 will be eliminated. So two phases will be eliminated. Only silicon will be present here. Here also same. So silicon Si solid will be the present along with the gas phase. So this is the outcome of the second case. The first case SiO2 plus gas phase. The second case silicon plus gas phase. Very easy. Okay. This is very easy. But this is also consistent with the phase rule. Because phase rule, it is better I actually keep writing. That is better. So it is better I write actually explain you. The phase rule, you expect how many phases? I said you will get the expectation from the phase rule. Answer from the phase rule. You will see you will have two phases. That when gas composition is made constant, maintained constant, and temperature is changed, then you have applied 3 degrees of freedom, and then you have only two phases. That I will show you, two phases. So two phases, you have got the answer also. In this first case, what is silica? SiO2 solid. Let me check. Okay, if I am correct or this. SiO2 correct. SiO2 solid and the gas phase. So two phases. And in the second case, Si solid and the gas phase. Two phases. Two phases. So next year. So it is also consistent with the Gibbs phase rule. So you follow this. Third part. Noting that reactions 1 and 2. Actually, this is 1. Even this is 1, remember. This is reaction 1. Actually, I have removed this. So, but you note this. This is the reaction 2. So, reactions 1 and 2. This is the 1. Reactions 1 and 2 are both exothermic. Decreasing the temperature to 800 Kelvin without changing the gas composition. What is the gas composition? You may write this two. You write PO2 is 9.4 times 10 to the minus 39 atmosphere. PN2 1.9 times 10 to the minus 11 atmosphere. Okay, without changing the gas composition, will push decreasing the temperature will push the equilibrium to the right hand side, to this exothermic reaction and decreasing temperature. So to the right hand side, in each case, eliminating silicon solid. Eliminating silicon solid. However, this is very easy. This moves this direction until silicon is eliminated. However, one of the two remaining solids, which are there? SiO2 solid, Si3N4 solid, and Si3N4 solid must also be eliminated. How we know that? One of these two, this and this will also be eliminated. How do you know this? This is from the phase rule concept. So in compliance, okay, wait a bit. Just wait a bit. Right, in compliance in compliance with the phase rule. With the requirement with the requirement of the phase rule. Let us explain this. This is important. Prediction from the phase rule. If you have this, okay, see, I follow this. If is, see how phase rule predicts that one of these two will also be eliminated. Silicon already eliminated. Silicon already we have considered to be eliminated. But of these two, thus another one will be eliminated. So total two will be eliminated. This phase rule predicts, that is the great, okay, that is the great great thing about the phase rule, great achievement of the phase rule. That it will predict one of the great achievements. Follow me. How we are ensuring that two will be eliminated. Two condensed phase will be eliminated, not one. See, follow. F is this is interesting. F is C minus P plus 2. Here F is what? What you have applied? Follow this. In maintaining the gas composition constant means PO2 constant, PN2 constant. 2 degrees of freedom you have applied, and temperature of the system is arbitrarily decreased to 800 Kelvin. Third, 3 degrees of freedom. What is this? 3 you have applied. For namely, you write the temperature PO2, PN2. F is 3. F is already from the problem you have applied 3 as 3 degrees of freedom. C cannot be changed. C cannot be changed. C is 3. What is 3? You can write, you know very well. Silicon, oxygen, nitrogen as before. As before. It cannot be. P the unknown. P is the unknown. Okay. Or P is how much? 2. That means one solid. Gas phase is always present. So how many solids are accommodated? How many solids are included? 2 total. One gas phase. So one solid. Means out of these 3 solids, 2 will be eliminated. That is one solid plus one gas phase. This is your argument of these two. One of these two, silica, SiO2 and Si3N4. Now who will be eliminated? That you have to take up separately. Like this type of equilibrium. Like this type of equilibrium, that is very easy. You can construct the equilibrium from this, just manipulation of this. So write that equilibrium. So consider, so to find which of these two will be eliminated, answer this. So next consider the equilibrium between SiO2 solid and Si3N4 solid to find which will be eliminated, which will be as temperature decreases. This is your new problem. This is actually, now you see, this is a problem inside a problem. So you have to consider this equilibrium between these two. This you can very easily write by eliminating silicon from this. You will get this. Let me write here. So let us write this. Since the reaction, Si3N4, write this nicely. Si3N4 solid plus oxygen gas goes to SiO2 solid. This is 3 SiO2 obviously, and this would be 3O2 plus 2N2 gas. What is the delta G zero? Call it equation 3. Equation 3 or equilibrium 3. This is 1, this is 2, this is the 3. How I got this? By from this data. No separate data is required. Eliminate this, you will get this. Delta G03 is what? How will you get delta G03? From this delta G0, the 3 times delta G0 of this delta G0, 3 times SiO2, this delta G0 minus Si3N4. Okay, one more. So minus this value, get this. Then you will get this 3 times minus 902,000 3 times, and then this is minus Si3. This is minus minus plus 7401,000 minus this also include plus 10.5 TLNT. Then again go back here for temperature term T term plus 3 times 174, 3 times 174, and minus Si3N4 means minus 403, minus 403 Joule. Okay, is okay. Is what? The result is what? Write nicely. Very important data. Minus 1965000 plus 10.5 TLNT. TLNT plus 119T. This is very important data. Delta G0 or delta G03 is right here, or delta G03. This data will be used number of times. Okay, so this is delta G03. Now tell me, can we give this from this here? I do one thing. I tell you what. Since I start removing these first few lines. This one, this also, remove this, okay. What? Star what? Since, okay, since reaction 3 this one, this reaction 3 is what type, what nature? Is exothermic. It's okay to? It's okay, I think it's okay. It is exothermic. So use your old logic, previous reasoning. If it is exothermic and you have decreased the temperature is decreased, so reaction will move to the right hand side, eliminating Si3N4 and retaining SiO2. Answer. So your answer is SiO2 and the gas phase. Two phase, two phase, consistent with the Gibbs phase rule prediction. Since the reaction 3 is exothermic, though it is 3 term, but this term is predominant. So exothermic, and decreasing the temperature will favor the reaction moving to the right hand side. So towards SiO2 side, and Si3 and 4 will be eliminated. So reaction 2 is exothermic. Let us write this: decreasing the temperature will push reaction 3 to the right hand side, eliminating Si3 and 4 solid. So overall, so both silicon already removed, now Si3 and 4. So both silicon solid and Si3 and 4 solid will be eliminated, leaving behind what? SiO2 solid alone as the stable phase, along with the gas phase. Gas phase is always present. Gas phase means which composition you maintain the composition constant composition. So this is the composition: PO2 9.4 times 10 to the power minus 39, and PN2 is 1.9 times 10 to the power minus 11 atmosphere. So this is actually the first part. I am removing this since this is already answered. This we answer. What happens if the temperature is decreased? This will happen. This is the answer. Finally, explanations are already given. So this is. Next, take up the opposite. If we increase the temperature from 1000 to 1200, what will happen? See, I already explained you what will happen. I tell once again. Since exothermic, as temperature increases, the reaction will be favored in the opposite direction. So both cases. So silica will the push in this direction to the left hand side. The silica will be eliminated, and similarly here Si3 and 4, SiO2 will be eliminated, and Si3 and 4 will be eliminated. So how many phases you will get? Yeah, only in both cases you will get silicon only one single solid phase plus the gas phase, 2 phases, consistent with the answer 2 phases. So this part is very easy. Okay, very easy. So sorry, in maintaining the gas composition, no? Acha, where acha. Okay. Acha, let me write this: in maintaining. I don't run. I'm actually making some here. This I am removing. Third part continued. So here you give how many star? I don't know. Double star. Here give double star and start here. Third part continued. Okay. The opposite. This part. Okay, this question we are actually this subsection we are actually answering. Okay. Okay. Or this case we are considering, and then we are answering this case only. Okay. That is what? In contrast, when the temperature is increased, to 1200 degree Kelvin, from 1000 degree Kelvin to 1200 Kelvin, without changing without changing gas composition, the gas composition, again you will note that what is gas composition? PO2 is 9.4 times 10 to the power minus 39 atmosphere. PN2 is 1.9 times 10 to the power minus 11 atmosphere. This is the gas composition. Without changing the gas composition, reaction 1 and 2, here is the 1 and 2, reactions 1 and 2 will both be shifted to the left hand side, eliminating what? Silicon, eliminating both SiO2 solid and Si3N4 solid, and retaining the silicon solid. So the final product is silicon solid plus gas phase, which has the composition already I have written. So I am writing once more. PO2 is 94 times 10 to the power minus 39 atmosphere. PN2 is 1.9 times 10 to the power minus 11 atmosphere. At what temperature? At T is 1200 Kelvin. This case, of these two cases, okay, subsections, the second one, the second case. First case already answer. In contrast addresses the second case, that is when the temperature is increased. So this is here, and this is the answer. So I am removing this already. So these two phases here also you get. So the final product is silicon solid plus gas phase means 2 phases. So P is 2. So it is consistent with the Gibbs phase rule prediction. So I am removing this so that there is no difficulty in reading this. So with this we have solved this problem. Next I will take up another and take up an supplementary problem. Okay, that's this I am giving you. Just I take 5 minutes break. Okay, just couple of minutes break. Okay, then I'll take up then this diagram will come into picture. This supplementary problem that is designed by me. Okay, I designed this supplementary question. This is not in the Gaskell's book, but this will help you to understand help you to reach the same conclusion through the construction of stability diagram suitably constructed. This I'll take up soon. Okay. Bapu, Bapure. Oh, will end now, just now. Wait a minute. So I think there is a supplementary part. Supplementary question. Where I have finished here. Where? Yeah. So one supplementary question will be taken up next class. I think this will not be taken up today. This will be fairly lengthy. So it is good idea that this supplementary question will be taken up next class. Okay. So this is about this. Okay. That will involve figure 2, the stability diagram. So it will take some time. So it is better I actually drop the idea for today. I don't take up this today. I will take up this one next class and we'll finish this. Then only we'll finish the problem 3 and then still 2, total 5, 2 more will be actually left behind and we will have to cover 2 more problems that we will do, okay, if possible next class. Okay, otherwise we take another extra class. Anyway, see you. So today we actually call it a day and thank you very much for your everything, for your cooperation, for your interest, patience, etc. So we'll meet in next class. Thank you very much. See you.